So I'm going to talk about 4 different pieces that we've been working on, and kind of march through from where we are now in automation to where we might get to. And so, as I was introduced, titles, Game of Thrones, students really are where I derive all my power. And they are, I'm really grateful for all the hard work that they put in, that without which I wouldn't be able to say anything. And also lots of faculty collaborators at Carnegie Mellon. It's really been a rich environment to do some really risky and exciting things around automation and energy. And so when I think about autonomous vehicles, and maybe this is the kind of causality, and maybe I should do regressions on this exact statement, but I think of them as a systems problem. I'm a systems engineer, so that I think I'm fitting them into the box that I live in, but I really think that they're a systems problem. And so we've done a whole bunch of work at Carnegie Mellon and at RAND and other places about electric vehicles and the transition to electrification and life cycle assessment and systems engineering. And I think of AVs as kind of the ultimate systems engineering problem. And we did a piece at RAND in 2014 on the kind of a guide for policymakers to understand this landscape. And since then, I and some colleagues have been expanding in different areas that we laid out in that piece. And so we start with this, right? And we talked about this before the presentation, is that we were doing so well, everybody. I'm not mad, I'm disappointed. And so road fatalities were going down and down and down. We had little bumps here in 2005. But this is per billion VMT, so this is not absolute. This is rate per billion VMT. And then in 2015, we had a rate increase. In 2016, it's only the preliminary numbers are up. But we're thinking around 40,000 road fatalities in the United States. 40,000 people die on the roads each year. And the rate is going up. Some of the largest percentage increases that we've seen in a long time. And that's troubling. And it's also quite normalized into our background. Right? So 40,000 people dying every year on the roads is, this is the plane I rode out on. Boeing 777. That's one plane crash every 80 hours. And so if we think about if that was kind of in our minds every 3.5 days, we might approach this problem differently at the urgency that we, in the safety community, kind of look at it. And so we have this big safety issue that's been going on for a while, and now it's getting worse. Why is it getting worse is that we love to like our friends' brunches while we're driving at 60 miles an hour. I like brunch, but I can also wait just maybe till the red light, not the red light, when I get home to like the pictures of my friends' brunches. So if you see, when you're riding in a car at nighttime, put your phone down and in your passenger seat, driver let them on the road, but look in the other lane and you can just see, kind of anecdotally, just glowing faces looking down on the other side of the road. It's terrifying, right? And so the research still has to be done, but the kind of preliminary attribution to these rate increases is distracted driving. And we'll know over the next few years, experimentally, with all of us as the beta testers. And so we have a safety issue. We also have an energy issue. Transportation energy has been about 28% of our U.S. energy consumption for a while. It's never been lower than that. I'm sorry, higher than that. So we're inching up on energy percentage as a total U.S. energy consumption. And so 92% of our transportation energy is powered by oil, and we have to deal with how we're going to continue to provide mobility services at minimal environmental impact and minimal cost going forward is another challenge of stuff that we have to work on. And of course, as a result of that, we have 27-28% of our greenhouse gases are from the transportation sector. So we have a safety problem, we have an energy problem, and we have a greenhouse gas problem. And in the greenhouse gas space, oh by the way, transportation is the hardest to deal with. And we in the kind of the climate and energy community have been kind of saying, like, yeah, we'll get to that eventually. And it's really time to get to it. And we know how to deal with the electricity sector. It's also hard and also potentially expensive. The transportation sector is much harder. And then if I put up here transportation emissions over time by transportation user, right? Light duty is that big blue. Everything else is above. And if we want to do 80% reductions of all of transportation by some year, everything above that dotted line has to fit underneath the line. And so we can't do anything in transportation, greenhouse gas emissions, without dealing with light duty. So we have a safety problem, an energy problem, and a greenhouse gas problem, and really a scale problem as well. And so when we think about driving, we can use the economics literature and the engineering literature to put prices on how much we value this. And the AAA numbers are, 57 cents a mile is fuel and depreciation and taxes and tires and maintenance and everything else, and there's an operating cost and there's variable cost. That is all ostensibly borne by the user. And then, of course, we have externalities, and some of our other work has quantified the externality values that NHTSA and EPA use for CAFE and applied them to certain policy problems. But if I just march through these pretty quick, I've paid, in Pittsburgh it's $2.60 a gallon, so I paid $2.60 a gallon. Outside of that transaction is oil security, which is almost entirely work that's been done by our colleagues, Paul Leiby and others, on the economic shock of an economic disruption from an oil price shock. So that's all wrapped up in oil security. And then air pollutants, so we breathe in particulate matter, it reduces our quality of life years. That's bad. Climate change, we can put a price on climate change with a range from the social cost of carbon. But then here's the big one, right? So this is something that surprised us when we multiply the numbers out. It's like, we've been working down here. And here, congestion is where there's a big cost. Now, there's a cost of people's time. And so how much, this is very much a philosophical question. Do I value time or do I value lung capacity? There's two different values of utility functions there. But still, the dollar value of time from congestion is huge, and the dollar value from crashes is huge. So we were thinking about it, and it's like, even if with this magic total zero life cycle, no oil car, this big overhang of social cost is hanging on the right here. And so that's where cabs, connected and automated vehicles, come in. And so we think about, can we reduce all of these in one, with one set of technologies? And so many of you know, and I'm going to go quickly through this so we can dive into details afterwards, but you know that there's 6 levels of automation, and I want to take this time to impart a lesson to the students here, is that never do this, right? Never say, I have a lot of words up here and you can't really read it, but I'm going to tell you what it is. So that is, you don't do that, okay? So I've taken this, and because I'm young and hip, quotation marks, I made emojis, right? So when I think about the 6 levels of automation, we're transitioning from who's in charge, who's driving, who's monitoring, and who's intervening, down this SAE levels of automation. And so we're kind of here, right? Ish. You can get a Honda Civic, kind of my type of car, my market segment, as it were, that has driver-assisted features, lane departure warning with lane keeping, forward collision warning with auto braking, blind spot monitoring, and other adaptive cruise control, other features that are helping the driver do things that they otherwise wouldn't do. You can start to get into here with like a Tesla, where 2 things are being done: hands off, feet off. And I can tell you, it's amazing. Right? So when you're in stop-and-go traffic, having the car deal with the lane keeping and the acceleration, braking, and steering is quite nice. But it's not. I wanted like the little sleeping emoji. It's not. I'm sleeping. It's not even that I'm texting. I'm ready to take control immediately. And not all of us are NASA-trained pilots that are conditioned to that environment. Right. So that's where we are right here, which is quite a dangerous horizon until we get to kind of robot world. So we're all beta testers. It's going to go through the next, Professor Schledover said maybe 30 to 50 years, we'll see. But as we march through this, they all affect the outcomes that I care about: safety, energy, and environment in different ways. So we'll start with the first piece. And so this is our first paper, which is about the early automation features: lane departure warning, forward collision warning and auto braking, and blind spot monitoring. And so we can understand how these might be affected with the different technologies. And these are just radars and sensors. You can buy these on a standard package car for a few $100s to a few $1,000s more. And so what we wanted to understand is what are these, how would these initial level 1 technologies help crash-wise and social cost-wise? And so remember, in this area, I'm thinking just what's happening in this line. And so our student, Corey Harper, and a colleague of mine, Chris Hendrickson, we set out to look at all the crashes through GES and FARS, and many of you who work in transportation engineering are familiar with these data sets. And our student coded all the crashes in all over the country and said, these are, in the algorithms in the paper, but these are how many crashes would be avoided if these technologies were effective at certain rates. And so if something said rear-end collision, it means that that may have been avoided had the rear-ending car had front-end auto brake. Okay? And we thought about, all right, so here, this is the data set, right? So there's a set of fatalities, some were cleaned out. This is the remaining. And so, you know, forward 14% could have been avoided with forward collision warning, you know, 6% from lane departure. This is for the injury crashes only. And then some for blind spot monitoring. Great. Okay, so now we have an idea of how many, where, when, what time, so we have all the detailed metadata underneath of that. And then we can think about, all right, is this a big deal? So the first thing we wanted to say is, like, is there any there? And there is there. Right? So of all crashes in 2012 is when this data were from, you know, roughly a quarter are related to these types of incidents. Right? So I'm not saying it would have been completely avoided, I'm saying related to these. And then 8% of injury crashes, but look, a full third of fatality crashes. And a lot of that from that lane departure warning. And if it was lane departure warning with lane keeping, I'm drawing a little bit of a gray line between the warning system and an active system. But let's just say that are related to these. So the interesting thing here is when we started to map these, it's not just a heat map of where people live. If I normalize these per 100,000 drivers, and we have it for miles and everything else, it's different sets of constituencies might care about this in Congress and other ways, where there are lots of fatalities that could be avoided that are at least associated with these technologies. And so we set out to do a pretty standard benefit cost assessment using these data and using some cost of the technology package, we analyzed the cost of the technology package and added up the social cost of these avoided crashes on kind of two ends of the spectrum bounds. The upper end was, okay, every single car in the fleet has these technologies and they work every time, right? And so that's the upper bound. The lower bound is like the IIHS, the Insurance Institute, put out some data and said, we have some data on claim reduction severity based on vehicles who have these things. So we mined that data, we made some relationships, and we said, if those data held to the national fleet, then we'll use that as a lower bound. All right, so great. The highlight of this study is lower bound is still positive, which means that even if they were kinda, you get $4 billion annually of annual benefit from avoided cost. A lot of that is the people not dying, right? That's important. That has a cost. And the technology cost is just how much was I willing to shell out to the dealership to buy these packages. So this is an instance where the user is bearing all of the cost and achieving a lot of the benefit, but still also pushing benefit to the rest of society. And then this is $4 billion at the low end, and it's $200 billion at the higher end. You know, this is probably one significant figure estimation, but it does mean that this is coming, right? Forward collision warning is already slated to be standard, but the other stuff is NHTSA is going to look at these, and we've already gotten calls and about this exact paper. Is these technologies will be regulated and enforced, and so that means that safety is going to drive why we're doing AVs. And so, if safety is driving, we kind of in the energy community are saying, like, well, maybe we should worry about energy a little bit. Let's think about how we can kind of add a rider of energy onto how we think about AVs. And so this next piece is that start of it, which is down here at the vehicle optimization level and design. And so automation has this ripple effect that starts at the vehicle and it rolls all the way up to national energy use. And so back in our old paper, we made some really wild guesses about where MPG could go. And really, once you get to 175, like nobody cares, right? So it's like when you get to 100, we're good, right? But still, as you get higher and higher up with now level 5, you have carbon fiber, single occupancy, dispatched cars. And the idea is that it totally changes the game, which is great. But still, we're down here, right? So we're down in the area of partially automated, conditionally automated driver assist functions that could drive better than I can. So I live on a street that has a stop sign at both ends. The whole street's maybe 400 feet long, and people try to go 40 miles an hour down this thing, right? So not a great use of gasoline, maybe a good use of time, but as soon as you're using acceleration like that, you're doing something wrong. So this is the EPA's urban cycle. And what one of our students did was saying, all right, EPA does not have a way to test adaptive or connected adaptive cruise control in the urban cycle or the highway cycle right now. Code me something, well, let's together think of a way that we can have a vehicle look at this cycle, know that it's coming, and make decisions as if it were following a car through the cycle. Now there's plenty wrong with that, is that it's following the cycle rather than actively going through the cycle. Sure. What our goal for this first paper was the simplest algorithm possible that we could hand to EPA and say, maybe you should think about this. And that's what we tried to do here. So this is a car following algorithm across the EPA cycles with a whole bunch of different cars run through Virginia Tech's fuel consumption model. And so the 3 different autonomous rule sets, or automated rule sets, I would say. One is like, keep a headway, right? Never let me get any closer than some distance. The other one is keep a speed or a time. And the other one is some simulation of connectedness. So it was tell the vehicle behind, tell me, the AV, what the car in front of me is going to do at some time variant, 3, 4, 5, 6, 7 seconds. So the longer the time variant, the more ability to have the course correct. So again, very simple algorithms. We have them in the backup slides or in the paper. But we just want to say, is there a signal? And so, yes, we found that depending on how you design these rule sets, you could either improve fuel economy of the AV, or you could degrade it by up to 10%. And so that's a little bit on the higher end, but still, even if it's degrading by 3% or 1% or 6%, it's now I have the ability to degrade my fuel economy just by having a rule set that says, you know what, be an aggressive follower, or be a follower that maximizes time. And why would a manufacturer and OEM do that? Well, if it's not in the EPA test, it's not in CAFE. It's not in CAFE, and it's also not in the sticker. So now it's not on my, I can't advertise it. So I have the choice, I'm the engineer in the marketing group, I could say, make this car more active and more fun to ride in, right? Or give it fuel economy benefits that the user will realize will probably not give us credit for, right? So without that regulatory carrot, we are likely to see rule sets and algorithms designed for performance rather than fuel efficiency, and we think that EPA should design for efficiency incorporated in testing. So we said, here's one way to do it. It's not a great way, but maybe blend and weight a 6th cycle. They have 5 cycles. Maybe you do a connected adaptive cruise control cycle. All right. We've done another little piece that says, what about other level 2 technologies? And we tried to use some of Professor Sladover's work and others to bound with some Monte Carlo assessments how different levels of penetration might affect platooning or efficient driving. But the challenges here is there's 2 challenges. One is that rebound is a variable that we have to take exogenously. So how much more driving would I do because my cost per mile is lower? And would I even realize it, and how much extra would I do? If I take the CAFE literature, it's between 10 and 20-ish%, but we really have no idea what rebound looks like in an AV world. And so this is a paper that we've been working on. The first set of reviewers said, come back when you have an answer that stays above 0, or goes below 0 and doesn't come back, right? So right now we have no idea, right? So this is work in progress. I'll come back to that. But now I want to get to a piece that it's in progress now, and still trying to work on. I'll spend a little bit the most time on that as well. And so, putting in early, and all our work says it's video. It's not to be confused with driverless cars, but there's lots and lots of social costs on the table right now with the stuff you can buy in a Honda Civic. Good. Now let's get to the fun stuff. Robo World, right? So now we're more and more having the ability to have the robot do the thinking for us. And this is my world. I'm sleeping to DC. That's what I want. I just want to get in the back and I want to sleep. But before we get there, right, so we might have some transportation engineers and planners here. I come from that world way back when, a million years ago. And so you have a city municipality and says, okay, let's lay out our lot. Parking lot's 9 by 18. This is an outdoor space. There's other configurations, but this is a standard configuration. I have this length, 9 by 18. Great. I have 14 parking spaces. Now all of a sudden I have conditional automation, virtual valet. You can get on a BMW, Tesla, and others. There'll be more and more common in the near term, right? So there's lots of kind of tech press that says robocars coming tomorrow. But virtual valet is in the near term. And so now a robot doesn't need to open a door, right? So now I restrike my parking lot in a weekend and get 4 spaces. If I have, but what does this mean for an engineer or planner? It means how do you think about the existing assets you have and what you're designing right now, and what would it mean in 15 years? Right? For sure, that parking lot's going to be there for 15 years. What can you get, and what do you have? Fine, great, restriping, news. But let's get to the very important part of this, which is does density increase because everybody's hailing shared rides? Probably. Does sprawl increase because everybody's going to work like this? Maybe. Right? So these are above and below zero. We don't know. We know the direction of each of these, but we don't know the relative magnitude, so then we can't come up to a final answer. All we can do is bound it and do some random draws. And so if we think about at a parking level, right? Level 4 and level 5. Level 4 is the car is driving by itself or driving on its own without me having to intervene in most but not all places. So maybe there's a dedicated lanes or dedicated corridors that these AVs can handle in. Maybe. Level 5 is really where you want to be, where it can go. But let's assume level 4, level 5. How will AV adoption affect parking, VMT, and emissions? And we took data from Seattle, and our student Corey and Chris are working with me again on this. And we had Corey take all the parking lots, the stalls, the occupancy rates, the prices, and the census tracts and blocks. And there's 55,000 spots in the downtown Seattle CBD. They have some occupancy rate. And we said, okay, if I have to pay downtown, average price $19, lowest price $7 for a day, and where can I send these cars to where it's free? And so we looked around Seattle. They have a nice data set online. We drew out some perimeters and said, these are free, unrestricted zones. We looked at the curb lengths. We made some, one step better than a wild guess of how many spaces there are in these areas, and then floated a variable of the existing occupancy as an unknown with a distribution. Let's just call it 50% open in the free spaces. And so the AV has a variable cost per month. Maybe I own it, maybe I'm renting it, maybe I'm the fleet owner. No matter what, it costs me energy and time or maintenance, depending on what's happening, to drive it an extra mile. So I can use that as a variable. So we started with some number, 30 cents, 27 cents, as the variable cost, fuel cost per mile, plus some additional depreciation. That's an additional piece of uncertainty that I didn't model here, but we have it modeled. So we built an agent-based model, or Corey built an agent-based model, and said, all right, now the agent knows prices downtown, it knows distances to the free zones, it knows occupancy, and it minimized the cost. And so here are the garage and lots that are downtown in red, and these are our modeled sample free zones. These aren't even everything. This is just like, we stopped getting free zones once we got all the cars that could be downtown. So these are real-world-ish numbered of spaces in the Seattle downtown area and surroundings. And so, instead of what happens now is that somebody drives downtown and they park, they get out, they go to work, they go to shopping, they go leisure. Now they get out downtown, the car goes up to the free space, and then it comes back to get them at the end. So now we have some additional VMT and other emissions and challenges from that little corridor. But I've now freed up a space downtown. okay, so you're saying, and this is what I wanted, I told Corey from the beginning, I said, I want a GIF for the internet that goes from 0 to 100. And I haven't gotten the GIF ready yet, because this is all still work in progress, so it could be completely wrong. So please don't worry about it, we'll get it right, because anything that hasn't gone through peer review yet is not ready for prime time. I'm just sharing it between friends here. So, 0% AVs, this is the existing occupancy rates for downtown. Those are real occupancy rates. There's a modeled occupancy rate for the free zones. And so now, all of a sudden, I introduce 5% of the downtown parkers as AVs, and I fill up my first zone of free parking. You can understand how this is going, right? Because it's going to minimize distance, it's going to minimize cost. The most expensive lots downtown will exit. The free lots will start to fill, and then they'll fill more, and then they'll fill more. And now, downtown is car-free, and your neighborhood is packed. Great. Maybe, depending on who you are. What about VMT and emissions? What we're curious about, and again, this is a very early result, is like total VMT is not that much of a spike, mostly because of the way that Seattle's characteristics are. There's not a lot of downtown commuters relative to other VMT, and the emissions are also very small spike, but still not insignificant. 2.5% if every car downtown traveled an extra 8-ish miles to go to a free site. But, if you're the city finance controller and you say, I used to have $150 million in revenue, maybe there's some tax component to that. Now it's all free and it's on my neighborhood. I got city council people in my grill about parking in my neighborhood, as well as I have lost all this revenue. Now you also might have what happens, especially here in California, you have kind of Waze routes, where you used to live on a quiet street and Waze is telling everybody to drive down your street. And so in this environment where you have, people, this street, right, and this street might be lots and lots of people per day that otherwise wouldn't have. So total VMT is not that big of a deal, but on your street, that VMT might be a problem. All right, and then so the good news is, downtown now you have lots and lots of acres. I asked Corey to kind of give us an acreage estimate, he's working on it. It's tricky because you have multi-level parking garages, but now you have valuable real estate freed up in the CBD. It totally changes the way that you would design and plan around a downtown area if you know eventually you would not need that parking. And again, we think, what happens if they were shared? What if there are some partial EVs? What if they are first mile, last mile transit? All those are pieces that we're working into the equation, and we also, of course, need to think about life cycle impacts, and this is just some of the latest non-baseload grid data. Here's California, this is Seattle. But if you're in St. Louis or other places where you have a higher grid, those are also questions of how you set up charging infrastructure and how the grid advances. Things I'm parking on the side for after. The last piece I want to talk through is about VMT and access. And we in the transportation community, we sometimes step back and don't, I'm making too much of a gross generalization, but I do think that there's a bigger trend that forgets the kind of the mission of transportation which access and some mobility. And sometimes, under full automation, we might be able to increase access, especially for underserved populations, and we need to weigh those values and weigh those benefits against any other things that we're going to have. So how much will VMT increase in Robo World? No idea. Right? So this is moving VMT per licensed driver, so I normalized it, and the spikes are kind of annually because I had to divide by 12 months. And then get real gas price. And it sure looks like, and the literature shows that VMT is quite elastic in the short run to gas price changes. And we've seen this back here, in the kind of the 2005, 2006 time frame. We said, wow, that's a lot of VMT. And then during the recession, we were all down here, and we're like, here's my think piece. We've reached peak driving, right? We probably wrote those, right? That happened, right? Don't let it forget that we wrote that. And now, we've had 20 months of record VMT growth, absolute, and on a licensed driver. So that's mainly a function of economic recovery and gas prices as well. But so the point is, what happens to that curve when we introduce shared automation, right? Do I drive less? Do I drive more? The shared mobility service driver that I brought here, the Lyft driver who brought me here today, he told me he did 30,000 miles last year on his Lyft, just on his Lyft car. That's quite a lot, right? That's probably double an average, U.S. user, right? 2 to 3 times more. And so, how many other people reduced their consumption by that much in order to make it even out of the end, right? So we have to. These are all modeling exercises that are going on here, and some of the work of Professor Shaheen and others, and stuff that Professor Bayan is doing, are really important to try to understand those signs and signals. But really, in the end, this is not going to be a revealed. This is not going to be a stated preferences problem. This is a revealed preferences problem. So we're designing for a future state for which we have no real understanding of the sign yet, but that's okay. We can design under deep uncertainty. When we think about some of the underserved populations that might have the ability to increase their VMT, we dug into the NHTS data and did some bounding. And so there are different categories in NHTS. One of them is, are you a driver? No. Okay. They have passenger VMT, but they're not driving VMT. And the other one is, are you a senior citizen by age? We know that, right? So we put that there. And then there's the last one. There's a little box that says, do you have a medical condition that restricts your travel? But we don't know what that condition is, but that is a checkbox there. And we're able to mine that data and understand that all 3 of these wedges travel less than their age and gender counterparts in the rest of the population. Right? So these are underserved, travel-restricted populations. Now, if you're a senior citizen, you maybe have different work and leisure activities than somebody who's not a senior citizen. However, there's still some latent demand there. So we know from the other literature that says that many seniors would travel more if they had the opportunity. So there's some pent-up demand here that level 5 autonomy would unleash. What does it look like? Again, I'm trying to get across that building some of these models requires some data mining, some algorithms, but not a whole bunch. But it does have you understand, is this a problem or not, right? So we've had people come to us and say, once all the seniors start driving, it's going to be chaos, right? And it's not going to be chaos, right? But it's not going to be 0. And so here are 1 year, right? I mean, if we just flip the switch and said, all right, everybody has level 5. How much VMT goes up for the 3 wedges that we had? We're leaving everything else constant. Again, so many assumptions here. But for wedge 1, with the people that are not driving, now they have the ability to drive, right? And maybe that there was a price incentive, but don't forget that we could potentially do excuse me, some sort of fair addition, right? So somebody in a city right now that is at a certain income level could get a bus pass. It's not out of the question to say they could get rides in shared ride services. So VMT could then move from public transit potentially to shared ride services. Then you have elderly, and then you have drivers with med conditions. And so it's really, these are 3 areas of pent-up demand. You add them all up and you kind of bound it. It's 300 billion extra VMT. And that's about 14% of that year's total. And so it's not 0, it's not 100, but it's something that would add some congestion, but also probably improve a lot of people's lives. And so this automation could increase travel access for these groups. We're digging into, kind of at the data, 1 step lower on the data level now for understanding regional impact and other impact. This is more of a transportation kind of travel demand forecasting planning exercise, but still it's thinking about what increased access means and what increased cost could come of it. And then, when I was talking with Professor Bayan in Finland, we were at a conference together. This is why you are all suffering through this. I happened to sit at his table, and we talked about what we're doing, and he said, oh, you should come to Berkeley. So it's not my fault. He's the one who told me to come. So he said, is there good VMT and bad VMT? And I have never heard something like this before, and I think this, yeah, there is, right? So, what is the social value of my marginal VMT versus the social value of somebody that is blind that needs to go to a place of work, right? So there's different values that we as engineers and planners will start to ascribe and at least calculate. And so there's ethical, philosophical, economics, social science that all kind of get wrapped up into that. And so does the extra 30,000 VMT from the Lyft driver, is that good VMT or bad VMT? I don't know. What are the emissions? What was offset? What was enabled? And so all of that needs to get wrapped up into our calculations of how we do this going forward. And so we think about, there's only 3 variables in this equation that we're working with. This is, I don't know if you saw on the interwebs a few months ago, Bill Gates said, I came up with this equation, and like, yeah, this is the equation that is in the Chi identity. It's been around for 20 years. Activity times energy use, intensity of the activity times the carbon intensity of that energy gives us CO2. And so many of you are going to be working in all 3 of these. Some of you are going to focus deep into one, right? So we need to know through a lot of research here and else places what VMT looks like as the transition is happening. We need to know through kind of vehicle simulation and autonomy stuff that we do and stuff that you all do here, how does efficient driving really affect at the real world city level? How does efficient driving affect the per mile energy use of an ICE and an EV? We kind of know, but let's start simulating it with real world conditions. And then finally, this is the kind of bread and butter stuff is, all right, what's the fuel look like? Professor Lippman said that there was hydrogen stations going in Berkeley. That's great. We've done all, we and he and everyone have done lots of work on life cycle assessment of hydrogen and biofuels and electricity. All that needs to continue and then some to really understand kind of the impact of all of these. So a little piece that we're starting that I wanted to introduce with Jake Ward and some other faculty and some students is, all right, now we're starting to get some data. So what does a shared AV or hailing ride services or shared AEVs, automated electric vehicles, along different pathways of that spectrum, what does it look like for vehicle ownership, energy use, grid, traffic? And so we have some data on kind of Uber and Lyft market entry dates by city. And we have data on who is purchasing vehicles and what VMT looks like, trying to tease out signals from those data. But more interestingly, probably for this crowd, systems crowd, is, all right, let's run some optimizations of, given what we know about shared ride demands, how do we optimize EV charging stations that minimize cost, distance, time, emissions, maximize some performance threshold, riders served, time waiting, right? So we can do all of that inside of some optimization. We have the data that Professor Work from Illinois, who was just here a couple weeks ago. We're using that data and some other data to try to apply traditional traffic and systems engineering methods to kind of the energy environment question, which is really where we tend to have a niche and try to focus on is, all right, if I'm going to build new wireless level 2 or level 3 charging stations or have a DC fast charge, where do I do this in a grid network to minimize the number of deadhead trips or headways or waiting time and maximize the revenue per station? So all these variables are floating that we can then run mini optimizations on each of these. It's going to be kind of a pain to get it all to converge. However, I do think that this is an important kind of overlap between, I think, the systems folks world and the energy folks world and the travel folks world, which is using the data that's starting to roll in from Uber and Lyft to then make these models to understand. City of Berkeley wants to put in lots more charging stations, right? So what is the marginal impact of those charging stations on VMT? We can start to model and measure that when we have in a shared ride environment. Okay. So lots of challenges could slow this adoption. And so the safety technology takes a long time to diffuse. We have airbags and seatbelts, even after regulation. Right now, it blew my mind, right? So I wanted to have some gifts in here. I didn't put the blow my mind gift in it. I would have put it right now, right? Which is, of the fatal crashes last year, half were not wearing a seatbelt, right? So that, if we had auto seatbelt, remember the old Toyotas that had that, if you had auto seatbelt, you probably get most of the benefit, much of the benefit that the early AVs would do. So how does the purchased vehicles that have these technologies diffuse through the fleet? And every day I see another kind of market report that says, 90% of the fleet will be AVs in 2012. I mean, like, none of that is possible, right? So from an engineering kind of queuing theory, we have another student doing this, is like, how long does this take? It takes a long time. Professor Sledover said it could take, to 2050 to 2070 to get a level 5 everywhere car for sale, right? So that, forget any other projections after that. If that's what happened, then we have a problem, because this is different from all the other work that we've ever done. And the work that we've done before is, we're at a battery cost this much now, we're going to model it, maybe it hits this target, we're going to be wrong, but we'll have a thing. We don't know when the first car is going to be for sale. And if it's, maybe it's going to be a shared ride service that runs in HOV lanes, right? Maybe it'll be shared ride services that run in campuses. Maybe it would be kind of level 4 cars that work almost everywhere, but are never allowed to driverless mode on certain days or certain times. So those are all possible futures, but if it's the Professor Sledover future, which is level 5 everywhere doesn't happen for 30 years, we have to still model that outcome. We have to then design infrastructure and energy systems and fuel systems around that outcome, and it's deep uncertainty. And we don't know how to do that yet, but we can take the methods that we use for deep uncertainty in climate and energy to kind of apply to this problem. And then, of course, privacy, security, hacking, all those things are, I'm just parking them on the side. Infrastructure investments, how do we prioritize? Should we lane widen? Right? These are questions that you will get as transportation engineers. Should we lane widen? Robocars are coming. I read it in the Washington Post, right? They're going to say this is coming. That's a good question, right? So you need good analyses to kind of make those investments and think about how transportation planning and engineering are completely changing. You all, as you exit into the field, have access to new data and new systems that the mass majority of folks that are working right now aren't aware of and don't know how to use. And so that's a competitive advantage for you, but it's also going to be a challenge on how do you make convincing arguments, and you're going to have to show with open data, scientific and engineering, solid methods that are able to convince folks of what you're talking about. And so how we use these data, I think of this convergence of transportation planning, engineering, and data science is really making this really exciting. But it also means that if you, kind of be a little bit negative, if you leave here not knowing this, that's bad, right? So make sure we're getting that. I'm sure we're all getting that. Good. And so, as I've said, AVs will be introduced because of safety benefits, but policy can probably guide the sign for energy. So we think about how do you create flexible and adaptive energy policy and transportation engineering policies that get you kind of in the area that you want, rather than looking for the optimal. This is all about the satisficing rather than the optimal. And the thing that I hadn't talked about is some of the work that we're doing on freight logistics, and it's not just in the ground, right? So we're going to put robots in the sky above your head with my book that I'm ordering. It's coming and it's going to be above your face. And so how do we deal with that from a societal perspective and energy perspective is part of what we need to understand here, and that also affects all of our freight logistics. All right, 2 more slides is smart policy would align the cost of benefits. Of course, this is very kind of rah-rah, everybody knows this, but learning what flexible adaptive engineering looks like, and Professor Denoy-Philip at MIT has done a lot of work on reliability and flexibility, you can apply those mathematically directly to this problem. And thinking about applying flexibility and sub-optimality and satisficing to this problem is how we're approaching it, and I think how many of you should think about approaching it. And what I didn't say here is the work that we do on climate and climate resilience is kind of the same message, right? So we say, if you're a civil engineer graduating right now and don't know about climate resilience, you're doing it wrong. Not only are you doing it wrong, you're failing ASCE Code of Ethics #1, right? Don't kill people and be sustainable, right? That's what ASCE Code of Ethics Canon 1, that's what it says. So you, just in that you will be a bad engineer not knowing about climate impacts, you also will be a bad engineer not knowing about automation. So just because we think it's coming maybe never in our lifetimes, or maybe a lot sooner, maybe there's a surprise event that says, hey, we figured it out, everything's cool now. You need to understand engineering-wise and research-wise how that percolates into your research talks. And so thinking about the uncertainty world and bringing that all into your analyses is how we've been approaching it. And so low regret, robust decision-making, and flexible and adaptive the policies and designs is where we think that this is going to go. So I appreciate the time, and I'll finish up now. I know that it's a holiday weekend. Everybody can ask questions, take off whenever you have to go. I'll hang out for as long as you want me to. But it's really an honor and a pleasure to be here at this fine institution, and I'm grateful for all your time. So thank you.